Okay, so we've heard a lot of really great discussion throughout the day on the technical challenges of next generation displays and specifically different hardware solutions to meet those technical challenges. I think that one of the other avenues to getting to next generation displays is also software. So how can you use software to reduce the technical difficulties of hardware? And so that sort of co-design is what we're doing with the SLMsuite software collaboration. And so we are specifically using spatial light modulators, or arrays of phase-based pixels, to generate far-field patterns. And we use this for a holography process because it can be very high efficiency, and it can also be very precise. The difficulty is that it's hard to do. We have to calculate what the pattern is in the near field that produces a far-field pattern that is the target image. And that image can be in different planes. It can be a three-dimensional image as well. So that's the reason why I think that the majority of industry has stuck to amplitude-based modulation techniques like digital micromirror displays. But with the software package that we've developed and are continuing to develop, you can generate images like we've shown in the slide here. So specifically, this entire slide minus the text is generated with a single spatial light modulator pattern. And so what that means is we have to calculate what the pattern actually is to produce the images on the left-hand side. These are sweeping through various focal planes. So you can see that some of the images are in focus, other ones are out of focus, and we're sweeping through the focus for a three-dimensional display. And then on the right-hand side is really what we focused on currently, which is spot-specific arrays. So targeted applications like optogenetics or optical tweezer arrays require very precise manipulation at individual points. And so what we're showing here is a Zernike pyramid. So we're actually tailoring the aberration profile of each one of these points individually. So our ability to tailor aberration in a spatially dependent avenue means that from a small display perspective, we can use higher numerical aperture optics, which typically have more spatially dependent aberration, to be able to generate patterns like this. And then on the top-hand side, you just see the repeated pattern of these aberration profiles, but now we're doing it with structured light as well. So all of this can be generated with a single spatial light modulator hologram, and the whole point of the software that we're developing is just that a user in any one of these other industries or the display industry can just say, here's the target image that I want to project. I'm not worried about all the computation that goes into it. Let the software take care of that. Okay, the way that we got to this software is actually, we developed the collaboration when I was a graduate student here, and we were focusing on building new spatial light modulators. So we started focused on the hardware, but every time we tried to build a new spatial light modulator, whether that is the resonant device on the bottom side of the slide here, or on the top side, a non-resonant spatial light modulator, we were required to generate some sort, thank you, we had to use a commercial spatial light modulator to make this work. So for the bottom side, for the resonant spatial light modulator, we had to tune all of our pixels to the same resonant frequency. And for the non-resonant spatial light modulator with lithium niobate pixels, we had to use a spatial light modulator to reconfigure the output of the device to target a atom array. So for both of these applications, we found out, wow, it's really hard to use a phase-based spatial light modulator or to do holography in general. So let's make a general open source software package that makes it easy for people to do this. We saw the same problems occurring in research groups across the Institute, and so we wanted to solve that. So this now features users across not only the Institute, but also the community at large. So it's an international collaboration. We've got hundreds of users, and we've produced a number of meaningful results with it. Since a lot of people have expressed interest and done a lot of really awesome work with micro LEDs, I want to focus on the software, but I'm also going to talk very briefly. I'll give you a pitch on the hardware that we developed, because this is an example where previously I discussed using spatial light modulators to make SLMs. Here we're using displays to make displays. But in this case, we're using incoherent micro LED displays to actually make coherent laser-based displays. So the way that this works is that you have an array of micro LEDs. So a micro LED display that then is able to control the resonant frequency of an array of optical cavities. So then if you reflect a laser off of this optical cavity array, then you can focus light on some target point. So this required a number of different innovations. How do you design the photonic crystal devices to be wavelength scale and high reflectivity? How do you manufacture it across a whole wafer? and then how do you control each one of the devices. So you can control them with micro LEDs through free carrier dispersion, but to do that, and this is just a picture of imaging the micro LED array onto our cavity array, but to do that you have to have all the pixels at the same resonant frequency. And so this is the actual application that we were required to, or required us to develop SLMsuite, which is we have to take an array of cavities which initially has a dispersion of resonant wavelengths on the order of a few nanometers, and we reduce that down to the picometer level. So because the thickness of the membrane is roughly proportional to the wavelength, you can think about this as controlling the thickness of the device to the picometer level. And that's possible using this holographic method where we trim each one of the devices thermally by applying some amount of power. So it's very high precision, and that's why we eventually developed this technique, because holography is hard. So in a typical holographic setup, again, you have a spatial light modulator that displays a phase mask, and then that gets projected into the far field, and there's very simple algorithms where you just bounce back and forth between the Fourier plane and the near field plane. But if you do that without compensating for the aberrations in your actual setup, then you get distorted images. So what you actually have to do is all the boring stuff that's in the red, that is the focus of our software, right? So you take care of all of the alignment, beam profiling, crosstalk compensation, and so forth, all of the technical details that have to be resolved. And really the point of this is it's a hardware-software co-design that gets to the fundamental limits of what the hardware performance is. That's our overall objective. And if you do that, then you can generate these very nice, clean profiles in the far field. That's what's required for not a lot of applications. We're specifically focused on optical focus arrays and tweezer arrays in the near term, but then those also push towards the requirements of future 3D displays. Okay, so this is just a general overview of the software that we're developing. So you can see here, and of course there's a QR code so you can actually go see if it's truly what I'm telling you. But you could see that the first thing that's required is we have to align the near field and far field planes. So we do a projection that calibrates the dimensional transformation that occurs such that you don't necessarily have to do that yourself. Again, all you want to do is project the final pattern that's required. You can then characterize what the phase profile and the amplitude profile of your source looks like. And then the entire first slide that I showed you can be generated with just a few lines of code, actually. It's just like using any other Python optimization toolkit. So very simple and straightforward. It's also GPU accelerated. So again, what we see is that every time we go to faster and faster hardware, we need to make sure that the software is co-optimized such that you can actually use the benefits of that additional bandwidth. It's also modular to a number of different setups. So in this case, we're showing a 3D display where we project light through a quantum dot solution. And the result of that is that there's a lot of spatially varying aberrations because you're going through a different refractive index environment. And so if you don't correct your hologram, then you can see on the top video, then you get defocused points, versus you can increase the depth of field significantly if you properly calibrate for those aberrations. One of the other trends that we're focusing on is how do you make sure in pursuing the fundamental limits of the display is how do you make sure you're using all of your degrees of freedom properly? You have millions of phase modulators in these devices, but typically the number of points that people project in the far field for holography is not 1 million points. So how do you get to that level? The way that this works is that typically you do a Fourier transform from your near field to your far field, which is what's shown here, except your far field is in the basis set of all of these different angular vectors, so steering in different directions. What we can instead look at is a compressed holography, which is when you realize that not every target point in the far field will have light. So if you have some sparse output pattern, then you can instead just project to those individual points. So here you've reduced your degrees of freedom from every far field K vector to just a certain number of N points, where capital N is that number. So we recently published on this, and you can show that this K is a kernel. The kernel for the Fourier transform is just a linear shearing operator. It's what produces diffraction gratings that are summed up to steer points in different directions. We can generalize that, though. Specifically, we can go from Fourier holography to Fresnel holography by adding quadratic phase patterns to defocus the points. And then if you extend this to an entire complete basis set, then you can individually tailor the outputs of every single different spot. So again, when we talk about going to a small display, typically what that means is shorter focal lengths, higher numerical apertures, and then more spatially varying aberration. Now we can tailor each point individually to remove that aberration. So we can make very cheap optics into diffraction limited optics. So this is what it looks like when we project a output pattern, or this is a laser tweezer array, where the tweezer points are all at the black sites. And what I'm showing here is actually the entire Nyquist limited far field of the device. What that means is the phase profile is going from pi to 0, pixel to pixel. So this is the entire range of information in the far field that you can display. So it's wide field of view. And you can see that if you don't correct it all, we have an intentionally aberrated setup here to try and demonstrate the capability. Then the points, wherever you go, are very aberrated. So what people typically do is they look at a single point in the far field, in this case in the center of the circle, and they say, I want to focus all of my light at that one point. And so you can do that, but then it's at the expense of the rest of the points. You don't correct outside of this center field of view. What our techniques are now allowing us to do in this aberration-space holography is that you can correct each site individually. So now you can get diffraction limited performance across the entire field of view in a very aberrated setup. And then, of course, you can also look at doing some more science-y things of what do the principal aberration modes look like and how do we compensate them in different ways. So overall, I think big picture what this points to is how do we combine not only next generation hardware, which has been, I think, the core focus of the event today, but also combine that with software. Because what we're seeing is that there's generations of hardware development that are going on, whether it's the liquid crystal devices that we're using now, the deformable mirrors of adaptive optics, or going towards more MEMS-based devices. A lot of MEMS spatial light modulators are being developed. The photonic crystal device I talked about, or even broadband spatial light modulators in the future. Every time we increase the bandwidth, we're going to have to think about how to do the compute optimally. And so that's what we're really interested in doing, whether that's hardware-specific optimizations or software-specific optimizations that really make the computation efficient. And so, again, that's starting with more near-term applications where we're projecting spot arrays, but the same exact principles can be applied in the long term to the very complex problem, both in terms of software and hardware of holography. So we're interested in putting more resources behind this development. Again, it's an ongoing collaboration, but we want to get more people involved and get more feedback. So if you're interested, please feel free to reach out. And with that, I'll take any questions.
Thanks for sharing your great works. Have you ever applied to a large size?
So it's extendable to whatever field of view you want to look at. So you can re-image. Typically, a spatial light modulator has pixels on the order of 10 microns or so. So it's only a few degree angular resolution that you have, or a far field steering. But you can just re-image those degrees of freedom into a much broader perspective in terms of angle. So you do that and extend it to a long range, then the display is going to be massive, but you have to understand that the number of degrees of freedom are still limited to the number of pixels that you have.
Yeah, am I right to understand that, right, it seems like you talked about the early hardware, but you're still going to be limited by the physical fill factor, right, of your SLM, like how much of the pixel is filled and how much spatial temporal control you have? Like, can you help me understand the limitations of the hardware on the software?
Generally, the hardware, so the result of non-unity fill factor is just that you're going to have lower diffraction efficiency. And so one of the corrections that you could do with software, for example, is figure out how much light you want to steer to the 0 order and at what phase you want to use to destructively interfere with that 0 order pattern to then increase the amount of power that you have to steer into other orders. So again, this just goes towards the idea of the co-design that we want to do, which is that there are hardware-specific limitations of each one of these devices, whether it's the crosstalk that's inherent in liquid crystal devices, or whether it's a non-uniform response, let's say, of the spring constant in these DMDs or phase light modulators. Now we want to use the software to correct for those, because oftentimes it's more difficult to perfectly correct the hardware.